Good morning everyone. So in the last class, recall that we have discussed shifting formula and we have seen how can we use the Laplace transform to solve the equation with constant coefficients. Today we will see that Laplace transform can be used for solving the other differential equations also. So to begin with, few interesting observations are, if I have to compute f dash p, which means differentiation of f of p with respect to p, and if I use the definition, then it is 0 to infinite, and f of x is a constant with respect to p, so differentiation of e raised to the power minus px is e raised to the power minus px and minus x. This becomes the Laplace of minus x f of x. Yes, even this gives us a very important observation which we are going to use it again and again, that Laplace of x f of x is minus f dash p. It means if you know the Laplace of f of x, then you can always compute the Laplace of x f of x by first computing Laplace of f of x, which is f of p, and differentiating it with respect to p and taking the minus sign. So it means if I repeat the process, then f double dash p would be Laplace of x square f of x. And similarly, I can say that nth derivative of f of p is Laplace of minus 1 raised to the power n x raised to the power n f of x. Now let us assume we need to compute the Laplace of under root x. I can do it by definition, but that requires a lot of time. Instead, what I can do and what I can recall, that I already know the Laplace of 1 by root x. Yes. Now think that how can you use the Laplace of 1 by root x to compute the Laplace of root x. It means if you see it as Laplace of x f of x, so x and 1 by root x, which is minus d by dp of Laplace of 1 by root x, which is root pi by p, and that gives you Laplace of root x is 1 by 2p root pi by p. So in the same fashion, we can try to see what would be Laplace of xy, xy dash and xy double dash. Yes, we'll use the same concept. So xy is straightforward, minus d by dp of Laplace of y. If I represent Laplace of small y by capital Y just for the simplification, then it is minus dy by dp. Now Laplace of xy dash, I already know what is Laplace of y dash. So minus d by dp of Laplace of y dash, which is py minus y naught. Y naught is a constant with respect to p. So it simply becomes minus d by dp of p capital Y. We need to remember all of these formulas so that we can use them to solve the differential equation. Laplace of xy double dash, again minus d by dp of ly double dash. Laplace of y double dash is p square Laplace of y minus py naught minus y dash naught. Y dash naught is a constant, so it would be minus d by dp of p square capital Y minus py naught. Now let's try to solve the following differential equation. Xy double dash plus y dash plus xy is equal to 0, where y naught is equal to 0. If you look at this differential equation without knowing anything, can you tell me the answer of this differential equation? So if you spend some time, you will realize that it is a Bessel equation. X square y double dash plus xy dash plus x square minus p square y is equal to 0, where p is 0. So Bessel equation of order 0, it means it has the solution j naught x. Yes. Now let's solve the same using the Laplace transform. So if I apply the Laplace transform, x y double dash I know, what is Laplace of y dash I already know, and Laplace of xy is again minus d by dp of Laplace of y. Now substitute all the values. Yes, substitute all the values and see how it, and simplify it. So if you simplify it, I'm not going into detail, but if you substitute all the values and simplify it, that it easily get transformed into first order differential equation. If I use the variable separable form, then I will get capital Y, which is Laplace of y, is c by under root 1 plus p square. If I take 1 by p outside, it would be c by p 1 plus 1 by p square raised to the power minus half. Clear? Now what's next? I need to find the Laplace inverse to have the value of y of x. Now if I use the binomial expansion, then the right hand side would be c by p 1 minus 1 by 2 p square and so on. And if I observe, then the first term is 1 by p, keeping c aside. The next is 1 by 2p cube and so on. Let's try to compute the Laplace inverse term by term. So L inverse 1 by p is 1, L inverse 1 by 2p cube. So I know that L inverse of 2 by p cube. Yes, so 2 by p cube is x square. So if I transform it into the form 2 by p cube, it comes out to be x square by 2 square. And if I keep doing it and substituting the values, I am not going into the generalization, but this is how my y of x looks like. Now it is given that y of 0 is equal to 1, which means if I substitute y of 0 is equal to 1, then the right hand side would become 1, would become c, and the left hand side will become 1, which means c is equal to 1. It means my y of x, which is 1 minus x square by 2 square and so on, would simply be j naught x. Yes, now what can we conclude? How did we get j naught x? So j naught x I got by taking the Laplace of 1 by root 1 plus p square. Yes, by taking the Laplace inverse of 1 by root 1 plus p square. It means Laplace of j naught x is 1 by root 1 plus p square. We will do some exercises when we can use the result Laplace of j naught x is 1 by root 1 plus p square, but time being you need to remember it. Next important result is Laplace of f of x by x. In today's lecture we may not be able to cover many exercises based on so much concept, so I will continue it in the next lecture, but today we will cover most of the theory. So Laplace of f of x by x is equal to integration p to infinity capital F of s ds. I can solve it by starting with left hand side or right hand side. Let's start with right hand side. So if I use the definition, it is p to infinity 0 to infinity e raised to power minus sx f of x dx ds. It means my s is moving from p to infinity and my x is moving from 0 to infinity. If I use the change of integration, it means either I consider the vertical line or the horizontal line, there would not be any change in the limits. So now in case of vertical line, the limit would be p to infinity and horizontally it would be 0 to infinity. So if I change the limit, then you can see that here now I can easily integrate. Here I cannot integrate e raised to power minus sx f of x dx. That's why I use the change of integration. And by doing this, I can easily integrate e raised to power minus sx ds. So it would be e raised to power minus sx divided by minus x, because integration is with respect to s. And the limits are p to infinity. Yes. Now in case of infinity it becomes 0 because minus s is there and s is going to infinity. In case of p it becomes e raised to the power minus px by x. So 0 minus e raised to the power minus px by minus x, which simply becomes f of x e raised to power minus px by x. And what it is now, it is the Laplace of f of x by x. This is what need to be proved. Again, we are not much interested in the proof, but there could be many interesting exercises based on this result. I am just going to discuss one in today's lecture, and remaining I will discuss in the next class. So let's assume that I need to compute the integration of 0 to infinity sin x by x. I have to use the Laplace transform. Okay, if you see this formula, then the formula would be Laplace of f of x by x. It is not integration of f of x by x. So let's try to compute the Laplace of sin x by x if I have to use the above formula. See what will happen. So Laplace of sin x by x is this one. So there I am stuck. But if I take p tends to 0 on both the sides, then I will get Laplace of sin x by x is equal to 0 to infinite sin x by x dx. It means if I have to compute the value of the integral 0 to infinite sin x by x, it is same as Laplace of sin x by x when p tends to 0. So it means in the standard formula also I can take p tends to 0. So this would become Laplace of f of x by x, and when p tends to 0 it becomes 0 to infinite f of s ds. Now I have to compute capital F of s, which is Laplace of f of x. Laplace of f of x is sin x. So Laplace of f of x is 1 by 1 plus p, 1 by 1 plus p square. So integration of dp by 1 plus p square, we already know it is tan inverse p. And if I substitute the values, it comes out to be pi by 2. Okay. So there could be many more interesting questions based on this formula, which we will see in the next class. Let's solve the last question, which says that solve the following differential equation using Laplace transform. So again the idea is to apply Laplace transform on both the sides. Apply it, do all the simplification. It's not difficult. If you do all the simplification, then you will reach here, which is a first order linear differential equation. Dy by dp minus y by 1 plus p is equal to minus 3 by 1 plus p cube. Now we already know the solution of first order linear differential equation. I have already mentioned here. So now for this, integrating factor comes out to be 1 by 1 plus p, and if you substitute the values, then this is how it looks like. Now I already know the integration of 3 by 1 plus p raised to the power 4. So I do the integration and take p plus 1 on this side. Now I have to take, to have y of x, I should take Laplace inverse on both the sides. Laplace inverse of 1 by 1 plus p square is 1 by p square is x, and using exponential function it is x e raised to the power minus x. So this is how it looks like. Now here the problem is, I know that y of 0 is 0. So if I substitute y of 0 is 0, left hand side would be 0. The first term x e raised to the power minus x would be 0 when x is 0. This gives me C L inverse 1 plus p. Now I assume that L inverse 1 plus p is non-zero. That gives me C is equal to 0. Also you can observe that Laplace inverse of 1 plus p does not exist, because recall that we have done the result when p tends to infinity. F of p is not equal to 0, then there does not exist a function f of x for which this Laplace exists. Example was p sine p raised to the power p, similarly 1 plus p. And therefore, we have no information about it. That's why we consider c is equal to 0. And that gives me y of x is x e raised to the power minus x. So that's all from today's class. In the next class, we will do many more exercises. Thank you.